interference of waves. Okay. Interference of waves and standing waves in strings and pipes. So this one introduces you to the physics of interference, which also is similar to the interference of light waves, right? And also standing waves, which is kind of the whole field of acoustics, which is the physics of instruments and noise and sound. Right. So in chapter 18:1, we talk about interference of waves. So then we're visualizing here, like let's say you have one source of wave and then another source of wave, and they are emitting the same frequency, right? So it's different than chapter 17 where we have general two sound waves of random frequencies and their loudnesses add up always. Here, if they're the same frequency, then there could be certain locations where they cancel each other destructively. So, right, same frequency sources of sound. So then they're emitting like this, and this one is emitting like this. Right, so wherever the peaks of the waves, coincide is constructive interference, right? And then whenever the peak of this wave is right in the middle of that wave, that's destructive interference. Destructive, 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 right? So this is constructive. So in the center, you're always going to have constructive interference, right? If you do this picture right, in the center should be constructive interference this way, because it's the same distance, equidistance. So if they start out in phase, so let's assume they start out in phase originally, they're being driven by the same oscillator. So we call that, in optics, we call that coherent light sources, right? And they have the same frequency. So then in the middle is going to be constructive interference. And off to the side, you're going to have a line of destructive, constructive, destructive. Then you're going to have the first order constructive, right? Then you're going to have second order destructive, right? And so this is called first order destructive. This is first order constructive. This one is the central constructive, central maximum.
Do you know why when we try to find the
this is second order destructive. You probably covered this if you're taking physics 4 this semester, right? So then what's the rule for constructive interference? The rule for constructive interference is that the path difference, the difference of the path from here to there and here to there, should be integer multiple of a wavelength of the wave. Right? For constructive interference, delta R should be what?
Yes. So it isn't like that.
N lambda.
It's actually like
right? Integer multiple of a wavelength where n is equal to 0, 1, 2, 3, 4, so on and so on.
Yeah,
for destructive interference,
so this is the velocity.
Remember what the rule is from physics 4? Delta R is equal to
And this is the velocity of
n plus a half of wavelength.
It's at a certain angle to this.
Where n is equal to
and it's
0, 1, 2, 3, so on and so forth, right? Or you know what, we could put it this way. We can write it as n minus a half, and then we wouldn't have any 0.
That's because you didn't say it.
Right? So any 0 would be central maximum, which is this one. Right? Central max. And then n is 1 would be this guy. See, n is 1, n is 0. And then if you add another maximum, it would be n is 2. Right? And then with the other color, we can denote the minimums. This one would be n is 1, first order minimum. So the reason I wrote this as n minus a half is so that I won't have any 0 for minimums, right? I'd rather have n is 0 only for max, and then I can say n is 1 is first order min, and then 1 minus half is a half. It's a half of a wavelength. So besides the central maximum then, it's the destructive interference that occurs first. Because you put 1 here, and you get 1 minus a half, right? Then here you put 1, you get lambda. Then you put n is 2 here, then 2 minus a half is 3 halves, right? So then it's the n is 1 for destructive occurs, then n is 1 for constructive. Then n is 2 for destructive, then n is 2 constructive. So the destructives occur before the constructives. This is constructive. And then the same thing on the other side, down here. Okay? In physics 4, you might have seen this equation that delta R, they write it as what? D sine theta, right? And then here delta R is also written as D sine theta. Where does that come from? You guys remember?
Right.
For in optics.
For the slits.
Yeah, so the D sine theta is coming from the distance between the sources, right? And then sine theta is they're taking, imagine that you have a laser beam, and you have a slit like this. So here, for light beam, we have the light beam coming, and then the slit, the light beam goes through the slit, and the slit acts as a point source of light. Here is a bit different for sound wave. The sound wave, the actual speaker itself is emitting a sound wave instead of being a slit, you see? But the idea is still the same. Then each one is emitting like this, like that, and then the same idea, right? Then we say, okay, the distance from here to here is R2. The distance between here to here is R1, right? Now, why can I use the equation d sine theta? It only applies in some limiting cases. It's not a general equation. This is more general than this guy. This is always true, right? So, when can I use d sine theta? Well, if the distance between the slits is small compared to the distance to the screen, you see? So if the screen was like up here, it wouldn't apply, d sine theta wouldn't apply. The screen has to be kind of far, right? And the distance between the slits needs to be small. So then you can say the distance between R2 and R1 is just this portion, right? In other words, R2 minus R1 is equal to what? Just this portion of the triangle. Because this guy, this light beam, has to travel an extra distance by this amount to get there. Otherwise, these two distances are the same. You see? So then the distance between the slits is D. This is D. This portion here is R2 minus R1. Right? And then sine theta is what? The sine of this theta, right? But notice the angles are different. This angle theta is slightly different than this angle theta. which theta are we using then? You see the idea? Is it the theta we're using from here to there, or is it from the upper slit to there? Well, the whole point is when the slits are close and the screen is far, this theta is equal to that theta approximately. So it really doesn't matter which theta you're using.
So small.
So you can say theta 2, theta 1 are approximately equal, and we're just going to call them theta.
Would it be more accurate to add them up and then divide it by 2?
Yeah, you can take their average, you know, and call it theta, and then you can say that theta is the angle from the middle of the slits to there, right? Instead of from either slit. And then you can still make, so imagine this is the slit and then this is this slit, right? So you can still say this angle theta will still equal that angle theta. They're all about the same, right? So then you can say this is the hypotenuse of that triangle. So sine of theta is opposite over hypotenuse. And therefore delta R is equal to d sine theta. Okay? So it only applies if the two slits are close and if the screen is far. And it only applies if the screen is pointing this way. What if we had a screen like this? And I wanted to know the pattern of maximum and minimums across that screen. Imagine I had a laser beam, my slit, and I had a screen here. Would it create maximum minimums? Yeah, of course. But the pattern would look very different than the pattern would on the board. And would this equation apply? No. Then I would have to apply this equation. Did you guys do that in the Physics 4 labs?
No.
Have it there, but then have a whiteboard here, and now measure where the maximum minimums are. Right? It's not a very often done lab, you know. But you would create maximum minimums like that. But the equation you wouldn't use this. So for sound waves, we're not even going to use this at all. D sine theta, d sine theta, right? Because for speakers, the speakers could be far apart, several meters apart. So it's just better not to even assume d sine theta, just to use dr, and then based on that do problems. Okay, so when we come back after the test, I'll do several problems using this equation.
Professor, I had a question.
Yes.
I don't understand the reasoning behind behind the velocity of the traveling. Let's say the jet, and then the sound. How the sound is perpendicular to the actual cliff, right?
The cone you mean?
Yeah, how it's perpendicular to the cone. I don't understand the reasoning behind that.
Let's see here. So imagine you are like this, and you created a sound wave like this, and now you're traveling like that.
Okay.
So by the time, sometime later, now you're going to make another cone. So now, the cone that you make is going to be tangential to the sphere of sound waves that you have made.
Okay.
Right? So I guess it comes down to understanding why you're making a cone. What does it mean to make a cone? And why is it tangential to that circle? Once you can understand that this is tangential, then you can say this is perpendicular.
Oh, okay. So
right? And then this is V sound times T. This one here is V source times T. They're both S. V sound times T, and then V source times T. So once you understand this is perpendicular, then you can see that, oh, okay, then you got theta here. Sine of theta is opposite over hypotenuse.
So that is kind of like a sphere. But if it is just a circle, that's going to be down.
I think even if it was a circle, like the video said, the bow, which one was the one that's on the sphere? Bow shock. Bow wave is on the 2 dimensions, it says. both shock was three-dimensional.
Mm-hmm.
So I don't think it matters whether this thing is 3 or it's just along the water surface. It's still the same circle.
Okay.
I think in this one it doesn't matter if it's 2-dimensional or 3. Does that help?
Yes.
Yeah. Yeah, that helps.
Good stuff, man. Okay, let's guys study your second test Wednesday. After that, party time.
Yeah.